Good morning. My name is Ashish Mahabal. I'm the Deputy Director for the Center for Data-Driven Discovery, and wear my hat as an ML person here for ZTF and for Roman Rapid. This is an ML and anomalies session, so we should have some fun things, how things are changing in particular. We have one talk that is invited and 3 contributed talks, and as usual, we have the discussion session. So let's start with Kostya.
Thank you. Hello, everyone. My name is Kostya Malanchev. I'm project scientist with Link Frameworks. Thank you, organizers, for inviting me to give this talk. So I was asked to talk about lessons I learned, and I decided to make this talk pretty personal. So almost everything I'll talk about will be from personal experience or from experience from the people I'm working with or was working with a couple of exceptions just to prove the point. So also, I assume that people thinking about this workshop as a more or less technical meeting, so it will be quite technical. Sorry for that in advance. So, okay, I will talk about few stories connected to my experience of working on machine learning and light curve analysis pipelines with bulk processing mostly, starting with data storage and data preprocessing and going to a couple of small thoughts examples on classification anomaly detection. So, and of course, this talk wouldn't be possible without all the people who I'm working with. So without SNAT team, Elastic team, and Link Frameworks. So SNAT is a collaboration for light curve anomaly detection. We started in 2018. And it's, seasonal collaboration. So we meet for a week every year and do some progress. And then they do almost no progress for another 50 plus weeks. And then we meet again. So the last meeting I was personally in person to was in Rio in 2024. And to prove it, there is a beach picture, of course. So I currently work with Link Frameworks as a project scientist, and we are a team working on, broadly speaking, software for large survey users. So if you're interested, please check our projects. We have a lot of projects. We have incubator program. You could apply and get 3 months with our software engineers to improve your software. So I will start with, I'm talking too loud. Oof, I should calm down. So with a pretty old paper we made with a small part of ZTF data as a use case to drive my other examples. So we selected some objects, we ran multiple anomaly detection or flash detection algorithms, and then we found that most of the things they output were bogus light curves caused by some artifacts or by other stuff, so asteroid going over the star or stuff like that. And it was a lot of challenges to make it work because of all the things we are going to talk about, starting with data storage. So for me, first work with a large data set started in 2019 during our second SNAT workshop in Claremont. So I have never heard about ZTF or about Rubin until that time. And then I learned about both of them in a couple of days. And this is how it happened. So ZTF data release 1 was released in May. And then I was like, oh, I will download the whole data set over API. ZTF people. Yeah. Oh, sure. Yeah. I'm sorry in advance about what I'm going to talk about, but it's getting only worse. So, it's almost 2 billion light curves, right? And I was like a hacker, right? I will do it in multi-threading because it will be faster. This is how I thought about myself. But actually what I did was DOS attack to Caltech APIs. I'm really sorry for that. I was young, and I think it was you are not killing me right now because it was a while ago. And I learned, and now I run APIs by my own. And I never do it again. So and then a couple of months, or maybe ZTF people remember better, bulk downloadable files appeared in custom textual format, which were pretty large, but it was much easier to get them. And what we did, like first, yeah, I'm going with the lessons after each slide or couple slides, like the DOS service is help getting what you want. Not really, please do not. And for catalog providers and for archival providers, it is really nice if you release catalogs in localizable form, so people could use it for machine learning and stuff. So then we have textual files, 2 terabytes of them. We wrote Python parser to go through them, but it's super, super slow. And you cannot query, you cannot filter. So then we we put everything to Postgre. I rewrote the parser in Bash. It was actually faster than Python by the factor of few. And then I was, I need to validate if I have all the data on my Postgre, and I will run count. And it took a week. A week. Think about it. So single, because Postgre was doing full scan. For data release 1, which is by modern standards, is not a large data set. Then we were we will use analytics database. So we chose ClickHouse, which is columnar database. It was much, much smaller in size. It could scan your data much, much faster if you do large scans. But it still was not super fast. So it was an order of magnitude improvement. It was an improvement. And we use it for a few data releases, I think for data release 2 and for data release 3. Then we found that we were still in this classical paradigm of SQL databases, of relational databases. We need to normalize our data and have 2 tables of objects and sources and join them. And it wasn't fast. And then we're we need to learn something about how analytical databases work and what best practices are there. And best practices tend to be to use nested column formats. So we have our light curves represented as, for example, MGD and magnitude column, of course, error, passband, and so on, not listed here to make it short. And I just selected, I don't know if you could see small letters here, but it's just a query where I selected 5 objects with 3 observations each, right? And that works much, much faster, and it is how industry practices recommend you to use analytical databases and analytical systems. You normalize the data, you put everything in a large table, and then since it's columnar based, if you don't need some column, you just don't read it. You don't even touch that part of your hard drive or SSD or whatever, and you could scan really, really fast. Okay, also going back to yesterday's broker panel, right? So sometimes you need, sometimes you need 2 systems to do the same job, because Postgre queries are still faster for single element queries than Postgre or traditional or document-based systems that are faster than analytical databases for single queries. So sometimes you need to support 2 systems if you would like to do both things fast. So use case is really important. So how could we port this experience of using analytical databases to make it available for users, right? For people who would like to have their database management system server running somewhere. So again, there is good industry standards and open source standards, for example, Parquet files and ZTF data release, I think starting with 5, started to release data in Parquet with actually nested list columns. So the same way we had it internally in our SNAT server for a while, and Parquet reduced the size, and what more important is you could work with it much, much faster. And generally speaking, if you don't need to do any special type of queries, you could just full scan it pretty fast. So you don't need a server anymore. You could access your data as a client and do all things on the client. And going back to, so if you could time travel, I don't see Time Lord here. Oh, yeah, so If you could time travel to yesterday, you could go back to Navistock and hear more about Heads LSDB. I will only briefly touch it, but basically what Heads does is porting all these ideas I was talking about to user land, right? So you could have Heads catalog as a Hevel provider or the end user. As an end user, you could access the data, whatever it is publicly shared, or is it on your hard drive, or is it like under the password of your collaboration? And you could do compute on your side. And also Parquet natively supports nested columns. So we don't need to do any like extra work and extra metadata to pack images like cursor spectra to Parquet FS. And also has optimized spatial queries as Nan was talking yesterday. So, and on the user land, we put effort to have nicer support of these nested columns. So it's a little bit small, but I will try to show it's here. So here we pack stuff even more. So we pack, for example, the whole SED into nested column. So not like we had before, we have separately, for example, fluxes and inverse variants, right, as separate columns. Now we have them under the same nested column. And then each element of this column is just, for example, spectrum, or it is a light curve. So we could have like multiple nested columns in one data set, and they are logically separated from each other. So it's more or less intuitive for users to understand that, okay, I will not like use fluxes from spectra with times from light curves, right? Even if I would be confused with the names, because I cannot, because flux is living under SED column and time is living under LC column. And with nested pandas, it is just a pandas extension. Again, it's not introducing any new storage formats or even storage metadata. It's just a layer over pandas, which supports all things is pandas support, because again, it's just an extension, which helps you to work with nested data sets. And nested pandas is integrated into LSDB. So you could do analysis really fast. So here, again, if you just listen for a part of Navistock when you try travel, please try travel again and listen about LSDB part. But basically, here just few examples of how LSDB could benefit from all the things I was talking about. So you see, for example, that here we have cross-matching performance, and these curves are all LSDB with a different number of workers. LSDB could parallelize cross-matching, and this curve, for example, yellow curve is AstroPy cross-matching, and LSDB could go out of memory, so it could go, you see, for larger number of rows, and it could run parallel, so you could have much better performance starting with something like 100,000 objects, because again, there is a trade-off. It's really hard to make a single system which works fast with like single queries and with bulk processing. And here trade-off is on bulk processing side. So, and when we ported this approach from server side to client side, we immediately have access, we give users access to use these technologies and to bulk process the data, not necessarily even collocated in one place. We don't have the problem anymore that one data provider should have all the catalogs you would like to cross-match, right, on their database. So you could cross-match them, right? So you could just on your like laptop get some data from one cloud, some other data from your department server, and some data you could have locally, right? And it will all work because all computations happening locally. Of course, again, as Navid said yesterday, data locality is still useful because you have I/O limits of how much you could do over the network, but at least you could do that. Okay, so going to few machine learning stories, and not with data storage for now. So when I was working on preparing the data for anomaly detection for ZTF data, I was also struggling with feature extraction from light curves. So that time we didn't use neural networks and all this. nice stuff. But also feature extraction is useful not just for traditional machine learning, but also for prefiltering. It's useful to have some features you could prefilter it to remove non-variable stuff, for example, or some bogus events or something like that, or like persistent objects through over transients, right? I found that existing libraries were really slow, so wrote my own library in Rust. And first it was just Rust package, which was like, going to the database directly through Rust and getting all the data. And it was like running. So it took like a couple of hours to go through the whole ZTF data release with some filtering, like filtering 90% of the stuff out with SQL and extracting some features from the rest of 10% of the stuff. And now it's used by please 3 brokers. Thank you, broker teams, for using it. Please report issues. I will be really happy to fix them and to introduce new features if you need them. And yeah, as we learned yesterday, not yesterday from Matthew, Rust is used for Babamu because, and I know it is sometimes scary to go to that direction because it could take a while to write stuff for performance, and you cannot know in advance how much time it will take, like your personal time to write the code, and going to new technologies is also could be painful. But what I learned from some of the folks working on Boom, that they don't really write the code. It's like AI writing the code or rewriting the code from Python to Rust. So it is less scary if you have AI helping you. Again, as we discussed yesterday, you don't have to trust AI, right? But it could like flatten learning curve a little bit. Okay, so next I'm going to a couple of open questions I have for the audience and for the community. So how do we do personalized machine learning, and do we do it? Who should do that? Should individual teams do it? Should broker teams do that? Should archival providers do something about that? So we heard yesterday from Gautam about similarity search portal, for example, for Dash, right? It is a good example of personalized machine learning as a service, right? Which you don't have to run on your own. So again, there is an example from SNAT work. So we were working, so after that paper I was showing in the beginning, where we found that we have a lot of bogus events, which our outlier detection algorithm provides us. It's not, of course, only our experience. I think everyone who was working with real data knows that this happens. And even if contamination of these bogus are relatively small, if they could be really weird, and that's why good outlier detection algorithm catch them, right? And also it is like, there is no good stats definition of anomaly. For example, what I observed in a lot of general anomaly detection papers, mirror stars are listed as anomalies, right? So, okay, maybe they're anomalous, right? But what if I'm not interested in mirror stars and I wouldn't like to see them again and again? And it's useful to have some human-machine interaction loop, and for that purpose, we built Coniferous package, which is doing tree-based active anomaly detection. And Think is using it for personalized anomaly detection model. So I'm not working on that Think model, but I was told that it's actually fitting the models for people who just, doing thumbs ups and thumbs down in a chat in Telegram or in Slack. And they're like fitting the models nightly for these people and making personalized experience for anomaly detection. And we also could do that with similarity search or with classification. So we could think about these things. Okay, the last thing is a really longer topic. What do we need classification for? So it sounds like a silly question, right? We know what we need it for, more or less. I mean, people have different use cases, but you need score, right? And if score is large, it is object for type you're interested in, you follow it up, or you adding it to your cosmological sample. But don't to be, so it's not my paper, it's Alex Moss, you could ask him he's sitting there, so that it's not necessary that algorithms which provide you good classification scores would provide you good performance for downstream tasks, for example, for cosmology. And another example is like that. So let's say that we have this green noisy image, right? And we ask our image classification algorithm, what is that, right? It says, okay, maybe it's grass, right? Or, okay, maybe it's a forest. And it gives like some classification scores, right? And we rely on them, right? So we're looking, okay, it's grass, so it's safe to step on it, right? And then when signal to noise goes up, we see something very different, right? So maybe it wasn't safe at all. So maybe we are not really interested in a probability of given type with respect of training data, given observations. And what we have seen in multiple research, don't have really time to go through that, but that your classification score could go up and down over the time with new observations. And especially it's getting even worse for small classes, right? Because if you have one detection, you just say it's supernova 1A, right? And it could get even worse if you provide some metadata. For example, you say, okay, there is a galaxy and it is like 5 arcseconds from center, right? Certainly supernova 1A. But then it turns to be something else. And for looking for like rare events, it could be a problem. So there's image from Griffin's talk, and I think it could be related to this problem. I'm not sure because I'm not sure how those machine learning algorithms work, but I think it could be related. Okay, thank you so much. That's all stories I like to tell.
Steph, for the wonderful talk, including some personal experiences. Questions? Okay, I see like there. It's coming from here. Oh, there.
Hi, thank you for the talk. So when you say, what do we need? Do we need classification? And my science, the scientist in me was like, okay, yeah, but we need to understand the classes of the transients to understand the physics of the transients, right? So,
yeah, but the question is, how do you use this number, right? Maybe we should have like a known class, and maybe we should track that when we're training algorithm, that classification scores could only go up. So maybe we should have like penalty term for that, right? For example, so it doesn't go like that, right? And if it is one observation, we don't say that it is 60% supernova 1A, we say 60% unknown.
Okay, I see.
Like with the green picture, right? So it's better to say that it is unknown.
Other questions? Until you think of a question, I had a question. So the anomaly telegram, that sounds great. So you said that it's mostly thumbs up and thumbs down on which the active learning happens, or are there additional things that are going in from the team also?
So I think, could you answer, Anis? Do you know more about anomaly detection board for Think?
Yeah.
So yeah, I'm not part of the project for the bot. They use library I co-developed. So.
Yeah.
Can you repeat?
Short answer, right? Because if there are questions, then we'll please. Yeah.
Sorry, can you repeat the question?
So what he mentioned is that there are thumbs down and thumbs up. Was it that people give based on which some of the classification happens? But are there other things that the team is internally doing, or it's mostly how people are scoring it up and down to determine whether it's an anomaly or not?
Yeah, so the model is trained using the features of the light curve, but the issue is that an anomaly for me is not what an anomaly looks for you. So for example, people looking at stars were very happy with the anomaly scores because a lot of weird stars were flaring. But me as a supernova person, I don't care about those. So the idea of the thumbs up, thumbs down was to help the model to find the types of anomaly that you're searching for without tweaking in the features, so you are only susceptible to a certain type of object.
Right. So there could be biases from different people, what they think anomalies.
Yeah,
yes.
But the model is personal, so it is your bias, and you're getting responsive for your model.
Okay,
yes, it's per person.
So you want that bias.
Yes. So this is not broadly deployed for everybody in Think. We are in beta user testing, so it's a handful of people that have personalized models.
All right. Did you have a comment or a question or? we're good? Okay.
Okay,
perfect.
paper to come soon. The draft is
Thank you.
there, so stay tuned.
Any other questions? Or we are nearly at time, so maybe we can hold it for the discussion later. Thank you, Costa, again.